So this is how we write our rate laws. Okay. And then what we do is we try to figure out these orders. So what are the exponents? We're going to talk about how to do that in a moment. Then once we know the orders, we can get the constant, and then we know everything we need to do. We can predict the rate of the reaction. You know, if we know these orders, we know these concentrations, and if we know that rate constant. But the first step, usually when you're doing a reaction, is to write the rate law for that reaction. And products don't go in. Rate equals some constant K, concentration of each reactant, and then raised to some order, which we're going to talk about. So how do we get these orders, and what are the possibilities? Okay. We got to do an experiment to get these orders. Tonight, you're going to learn the initial rates method for determining these orders. And our lab tomorrow uses the initial rates method to determine the order for a reaction, the bromination of acetone. So what can these values be? Well, in Chem 102, okay, these exponents are always going to be a 0, a 1, or a 2. Okay, in our class, they're always going to be a 0, a 1, or a 2. Okay, our reactants are always going to be 0 order, first order, or second order. Okay, in the real world, they don't have to be 0, 1, or 2. They can be way more complex. They don't even have to be a whole number. So in the real world, you could have a 0.5 order. You could have a 0.3333 order, right? You could have a 1.333 order, right? Okay, they don't have to be 0, 1, and 2. Now, most often they are 0, 1, and 2. Okay, so that's what we're going to deal with here in Chem 102. We're not going to do super crazy stuff. I'm going to show you how to use logarithms, okay? But usually you can figure it out just by looking at it because you know it has to be 0, 1, or 2 in this class. Okay, but I'll show you the logarithm method, especially tomorrow in the lab, because in the real world, the data doesn't come out pretty. And sometimes it can be hard to see if it's 0, 1, or 2, and you might want to use a logarithm to figure it out. Again, not a big deal. I'll show you how to do that when the time comes. So let's talk about these options of 0, first, and second order. Hang on, let me go back a couple slides. All right, so here are your options. If a reactant is 0 order, then essentially what we're saying is that reactant does not affect the rate of the reaction. A 0 order reactant will have no impact on the rate. What that means is if this reactant were 0 order, because anything raised to the 0 power is 1, it doesn't matter what this concentration is. If this concentration is 2 molar, well, 2 to the 0 power is 1. If I double it to 4 molar, well, 4 to the 0 power is still 1. That rate will not change. So if something is 0 order, what I would jot down about that is that a 0 order reactant has no impact on the rate. A 0 order reactant is not going to affect the rate at all. This reactant, okay, does not affect the rate. We'll talk about the kind of reactants that do that. Tomorrow, one of the reactants in the lab will be 0 order. And then we'll eventually, probably on Wednesday, talk about, how that's probably not involved in the rate determining step. Then you probably have a multi-step reaction. Don't worry about that for now. Let's talk about what happens if this order here is now first order. So let's say a reactant is first order. Well, a first order reactant, whatever you do to the concentration, it's going to have a direct impact on the rate. So, for example, if I run this reaction and my concentration of A is 2 molar, well, 2 to the first is 2, so my rate would be, 2. If I double that to 4 molar, well, 4 to the first is 4. Now the rate doubles to 4. And you can see I doubled the concentration. I would double the rate. So something that's first order, whatever you do to that reactant's concentration, you'll do the same thing to the rate. So if I double the concentration, I double the rate. If I cut the concentration in half, I would cut the rate in half. If I triple the concentration, I would triple the rate. So first order reactants are easy. Whatever you do to that reactant's concentration, you do the same thing to the rate. If a reactant is second order, this gets a little more complicated. You're going to have an exponential impact on the rate. So for example, say that the concentration of A is 2 molar. Well, now 2 squared is 4. But what if I double that? What if I go to 4 molar? Well, 4 squared is 16, right? I have now quadrupled the rate. I went from 4 to 16. right? What if I, I mean, it just keeps going from there, right? What if I had tripled this, right? Well, 6 squared is 36. So I would quadruple that again. Okay. Um, so yeah, the rate just keeps changing exponentially based on that. So a lot of times you can just look at a set of data and figure out if you're zero first or second order. For example, here's a set of data that is zero order. So let's imagine that we have this rate law. Let's imagine we have rates equals K times the concentration at A to the X. Okay. This is what it would look like if reactant A was zero order, where if I run the reaction 3 different times, and I have 0.1 molar A, 0.2 molar A, and 0.4 molar A, what you'll notice is that nothing happens to the rate. The rate is the same for all 3 trials. So if the amount of A doubles, notice that the rate didn't change. If I double the amount of A again from 0.2 to 0.4 molar, rate stays the same. So what this data is showing is that this kind of reactant, whatever I'm doing to it, not making the reaction speed up or slow down, so it must be zero order. If a reactant was first order, you get a set of data like this, where I run the reaction at 0.1 molar, it goes off at 0.015 molar per second. Now I'd run the reaction again, but I double the amount of A in there, and now the rate has doubled to 0.03. So double the concentration, double the rate. And that's what first order is. First order reactants, they have a direct dependency, right? So whatever you do to the concentration, you do the same thing to the rate. If I double that concentration again from 0.2 to 0.4, notice the rate once again doubles from 0.03 molar per second to 0.06 molar per second. So that's what some data would look like if something was like first order. What if something's second order? Well, now when I double the concentration, I have quadrupled the rate, right? I go from 0.1 to 0.2, that's double. And here I go from 0.015 to 0.06, that's quadruple, right? So I multiplied that by 2, and then the rate got multiplied by 4. And then what happens? Well, if I double that concentration again, I go from 0.06 to 0.24, I quadruple the rate again. So something that's second order, whatever you do to the concentration, you do whatever you do to the concentration, you have an exponential increase in the rate. Okay, so it's whatever you do to the concentration squared, that's going to happen to the rate. So a lot of times, if the data is perfect, and you got to remember in the real world, you don't always end up with perfect data, right? So like instead of 0.24, maybe you got 0.2173, right? Okay. So if the data is perfect and you get exactly what you're supposed to, a lot of times visually, if you know it's between zero first and second order, you can just look at it and figure out like which one it is. But sometimes it's not that easy. So I want to teach you this method where we put the rate law of one of the trials on top of the rate law for another trial, and we can solve for it that way. So I will show you that with the initial rates method. Give me 1 second, and then I want to show you the logarithms too. So this reaction has one of these reactants being zero first or second order, and then one of the reactants is not zero first or second order, which I would not put on a test. Okay, but I want to still show you how you would do it. We are going to do it in the lab tomorrow using logarithms. So if you give me a second, I'm going to write all this data up here on the board. You might want to rewrite this data table on a piece of paper as well. This is going to take about a sheet of notebook paper here. Let me show you how this is going to work. The number of trials that you have to do in an experiment is always one more than the number of reactants you have. So this actually is an extra trial. Trial 4 here is actually not going to be needed. We'll talk about what trial 4 is not needed, but I have it on here to show you that sometimes these problems, they give you more information than you need. The first thing we should do, though, is write a rate law for this reaction. So this is a reaction between chloroform and Cl2. You don't know what the products are, and it doesn't matter, because in these reactions, the products don't matter, right? So the first thing we need to do is write a generic rate law for this reaction. So that's going to be rate equals some constant K times the concentration of each reactant, CHCl3, that's going to be raised to the X, times the concentration of the next reactant, Cl2, and that's going to be raised to the Y. So there's our generic rate law for that reaction. Now, what I want to do is show you this initial rates method this way that we have for the initial rates method to set up a reaction. Okay, you could probably visually look at trials 1 and 2 and figure out the order for chloroform. Let's talk about why. You can only figure out one reactant's order at a time, because when you run a reaction, you can only change one thing's concentration at a time. You must hold every other reactant's concentration constant. This is common sense. It's kind of like a control in science, right? So if I change more than one reactant's concentration and the rate changes, the reaction gets faster, I don't know much. Here's why. Did the reaction speed up because one of the reactants was first order and the other one was zero order? Did it speed up because they were both first order? Did it speed? So like, does one thing have an effect on the rate? Do they both have an effect on the rate? Like what's doing? So that's why you can only change one thing's concentration at a time. So if we look at trials 1 and 2, trials 1 and 2 keep the amount of Cl2 constant. So we know that if the rate changes, it was not from the Cl2, but it changes the amount of CHCl3. So by only changing the CHCl3, we know that if the rate changes, it was because of the CHCl3. Now we could visually pretty much get this. What's happening between trials 1 and 2? Well, the amount of CHCl3 is doubling. It's going from 0.01 to 0.02. Okay, what happened to the rate? Well, the rate essentially doubled as well, right? It goes from 0.0035 to 0.0069, right? 0.0070 would be double. That's close enough. We should anticipate that this would be a first order, okay, dependency on the CHCl3. So X should be first order. Okay, so this one we can actually like see. Okay, but I want to show you how to do this if you can't see it. Okay, and what we do is we take the rate law for one of the trials and we divide it by a rate law for the other. Now, it doesn't matter which one you put on top and which one you put on the bottom, but I like to put the one with the bigger rate on the top. Because if you put the bigger rate on the top and the smaller rate on the bottom, you'll get a whole number. Like you won't get a decimal. Okay, you'll at least get a whole number. So, and it's usually easier to do like exponents with whole numbers than with so for example, if I say what's 0.125 squared, well, that's harder than if I say what's 2 squared, right? So we like to work in whole numbers. People tend to get the answers right. So what I would do to get the order with respect to X mathematically, not just visually looking at it, we're going to take the rate law for trial 2 and we're going to divide it by the rate law for trial 1. So let's write the rate law for trial 2. That's going to be the rate, right? The rate. So that's going to be 0.0069 equals some constant K times the concentration of CHCl3 for trial 2, 0.020 to the X, times the concentration of Cl2 for trial 2, 0.010 to the Y. So that's my rate law for trial 2. And now on the bottom, I want to put the rate law for the other one, which is trial 1. So that's going to be the rate for trial 1, 0.0035 equals K, some constant, times the concentration of chloroform in trial 1. So that's 0.010 to the X, times the concentration of Cl2, 0.010 to the Y. Take a second, catch up there, and we'll talk about what's going to happen mathematically here. All right, what happens mathematically here? Well, because we kept the Cl2's concentration the same, we have 0.010 to the Y divided by 0.010 to the Y. That cancels out. And we don't know what K is, but we know it's a constant, so that cancels out. So what are we left with? We're left with 0.0069 divided by 0.0035 equals 0.020 over 0.01 all to the X. So I'm actually going to punch this in. So we're going to get 0.0069 divided by 0.0035. That's going to be 1.97 equals 0.02 over 0.01, 2 to the x. And this one's pretty darn apparent. We don't need logarithms for this. 2 to the what power? 0, 1, or 2, right? Those are options in this class. 2 to the what power gives us essentially 2. Well, to the first power, right? So x must be first order. So this is how you would write it out mathematically, right? If you're having trouble visually seeing it, right? And I'm a big fan of showing the work, right? Because if you tell me the order on a test and you don't show me any work, you get it wrong. I can't give you partial credit. But if you just do this, go through the motions here, write it out, right? And if you somehow get it wrong, well, at least you kind of like set it up right. You just, put second order instead of first order. I give you some points. Okay. So what we just figured out is that the chloroform has a first order dependency. We know that X is 1. Now the Cl2, I've chosen this problem on purpose because I want to show you, some of you may be going on in chemistry, right? Okay. And you don't always get 0 first or second order. Also in the lab tomorrow, it's not going to be nice data, right? So I want to show you how to use logarithms. So the Cl2 concentration, I'm going to warn you, this y value is not 0, 1, or 2. Okay, it's going to be another value. Again, on the test, it's going to be 0, 1, or 2. So this is not test level. This is above test level. Okay, but I want to show you how we would do it. So I want to set this up, and I want to solve for the order with respect to y. So what we need to do is, because we're trying to figure out how the Cl2 is affecting the rate of the reaction, how does this reactant affect the rate? We need to pick a different set of trials. So we need a set of trials where the amount of Cl2 is changing, but the other reactant, CHCl3, is staying constant. And if you look at this set of data, that's what trials 2 and 3 are going to do. If we look at trials 2 and 3, the amount of Cl2 is changing, but the amount of chloroform is staying constant. And that has to be what's going on. We can only change one thing's concentration at a time. If we change more than one thing's concentration, then we don't know what's affecting the rate. Now, if you look at this visually, you can see this is not going to be good, right? So I'm doubling the amount of Cl2, but that's not staying the same. That's not doubling, and that's not quadrupling. So you can visually see that we are not going to have 0 first or second order here. It's going to be something more complicated. How do we solve for this mathematically? Okay, you're going to take one of the trial's rate laws, put it over top of the other one. I would put trial 3's rate law on top of trial 2's. Why? Trial 3 has a higher rate than trial 2. So I would put trial 3's rate law on the top, and I would divide it by trial 2's rate law. Why don't you take a second to see if you can just write it? I don't need you to do anything canceling out or anything. Can you put trial 3's rate law on top of trial 2's rate law? Give it a shot. All right, this is what you should end up with. We've got the rate law for trial 3 on top of the rate law for trial 2. Now we can start to cancel some stuff out. So the rate constant, whatever it is going to cancel out. And then the all of the data for chloroform is going to cancel out because we held the chloroform constant. Now we actually know that this is first order, right, from before, but you can just leave it as x's. That's going to cancel out. So what this is going to reduce down to is 0.0098 divided by 0.0069 equals 0.02 to the y divided by 0.01 to the y. So let's punch this in. So 0.0098 divided by 0.0069. That's 1.42 equals 2 to the y. And what you can see is we got not 0 first or second order, right? If this was 0 order, 2 to the 0 would be 1. That's not 1. It's 1.42. If it was first order, 2 to the first is 2. That ain't 2. And if it was second order, 2 squared is 4. That ain't 4. So this is something other than 0 first or second order. Now, how do we get it? The way we get it is to use a trick of logarithms. So what you want to do, we'll do this in the lab tomorrow, is you're going to take the log of both sides. I know, don't freak out. It's going to be okay. People hear logarithms, they start hyperventilating. They get like a flashback to high school trigonometry, I guess. And I can tell you, my high school trig teacher wasn't great. I don't think I really knew what a log was till college. But it's okay. You don't even really need to know what a log is here. Just need to know some tricks. Okay. If I take the log of both sides, what that does is it brings that y down in front. And what this becomes is it becomes the log of 1.42 equals that exponent comes down in front. Y times the log of 2. You don't need to know why. Just need to know that's what happens. And now what you can do, you can punch it on your calculator. So the log of 1.42, that's going to be 0.152 equals y times the log of 2, which is 0.301. And now we want to get y, so we're going to divide by 0.301. And 0.152 divided by 0.301, y equals 0.5. So the CL2 is half order, one half order, or 0.5. Okay, so again, I'm not responsible, but I want you to see how you would actually get it in the real world. Okay, you would use this method. Now what you would do after this, we're not going to do it until we get back from break. We're going to do it with another one where everything is 0 first or second order. What you would now have to do is, once you know the orders, you can now solve for the rate constant k. Okay, how would you get the rate constant k? Well, now that we know the orders, we could pick any one of these trials, even this fourth trial that we didn't need. You can pick any one of these trials as long as they're run at the same temperature. Okay, they got to be the same temperature. If they're at different temps, you can actually get the activation energy. That's the topic of Wednesday. But as long as they're run at the same temperature, you can pick any one of these trials, plug the data in, okay, and then you could solve for the rate constant k. Okay, so it's pretty awesome. Pick any one of them, right? So you would like plug in 0.0035 equals k times 0.01 to the first times 0.01 to the half, and you could solve for what k is. So every one of these initial rates method problems kind of operates the same way. First thing you got to do, find the trials that allow you to get the orders. Solve for the orders. And then once you know the orders, go back and solve for the rate constant using any one of the trials, as long as the temperature had been constant.